Hello. Wow. There you go. I knew GCC drama would come in handy one day. Project to the back of the room, the teacher would say. Or channel your inner Martin Fowler. That's the other. Hello. There you go. Morning. Afternoon. How's the conference been? Perfect. Awesome. Awesome. And I'm between you and beer, so I'm aware of that. So hopefully this will be an interesting 50 minutes or so. So the talk is called How Work Works. It's really basically a deep dive into what's going on in my rather strange brain at the moment. A bunch of stuff I've been thinking about for a while. Things like how to optimize the way we work. A bit about some interesting ideas from complexity science. Some fun things around things like generative science. So using agent-based models to look at if we can understand about the nature of reality using ABMs. There's some stuff in here about, I guess, where we've come from the last 10 years. And there's some stuff in here which I think is answering the question about, are we now software engineers? So there's a whole bunch of content, and hopefully you'll enjoy how work works and other curiosities. Now, I mentioned the curiosities. I have a few curiosities in here. Such things as whether this works or not is the first curiosity. And that doesn't work, so that's excellent. It did work a minute ago. There we go. The surprisingly recent invention of all the things. Now, Daniel Terhorst-North, if you were here this morning, he was talking about actually how a lot of the things we take for granted were invented a long, long time ago, talking about Dijkstra papers from the 70s and the 60s, and I've talked about Conway's Law and things, but actually a lot of the things we take for granted as of now are surprisingly recent inventions, so I'll cover that a bit. I'm also going to just do this instead. Why AWS and self-service ate your lunch, right? If you're in an ops team in your big traditional organization 15 years ago, AWS happened, you're probably not in that ops team anymore. Why is that? Why is it so successful? Are we engineers now? That's a brief aside. Just as a, something a bit of a change of pace, we'll talk about phase transitions in oligarchic societies, because why the hell not? And, the failure or impossibility of trickle-down economics being a success. We'll talk a little bit about why traveling slower sometimes makes you go faster, which seems a bit counterintuitive, but is a thing. Also, and I promised in the look at that. Thank you. Also in the abstract, I think I promised this thing about why batches, small batches, why you should leave thinking about small batches. So I'm going to tell you what Lego has learned about small batches, and I'll take that one. Thank you very much, Preben. It's like 1 in 3. And how work works. Maybe I've to turn everything else off. That's not how any of this works. Right, so how work works. But first of all, I'm going to start with this sort of idea of the surprisingly recent invention of all the things. So, I'll start with a quote from a great film, which is that life moves pretty fast, and if you don't stop and look around once in a while, you might miss it. So I work for Thoughtworks, as I've sort of banged on about probably over the last couple of days to anyone who would listen. And back in about 2011, we started publishing something called the Thoughtworks Technology Radar. And in that, every 6 months we get together. There's about 22 of us, 23 of us or so. And we talk about the latest, greatest, newest, most interesting things that are happening in the world of tech. Tools, techniques, platforms, languages, and frameworks. And every 6 months, we have about 300 new things to talk about. Every 6 months, we talk through every single one, and that might range from the latest, greatest JavaScript MVVM library to, some kind of like marshalling and unmarshalling thing for TypeScript, through to Kafka, through to new forms of testing and so on. Bearing in mind that's 300 new things every 6 months, and even before it comes to us, the individual countries who are representing in this group, they actually pre-filter. So India alone normally have about 400 new things proposed to them by their teams every 6 months. Now, if you think that technology is moving fast, if you think that there's so much stuff happening, it's kind of true. You know, if you think about how much stuff is happening every 6 months, it's unbelievable. And I thought I'd go back and go a little bit backwards in time to kind of take a look at where some of the things we take for granted now came from, and when they sort of first started appearing on our radar. So Android, back in 2010 or so, it was the first time anyone really was starting talking about Android. Git, same, or rather distributed version control systems. We were only starting talking about Git and Mercurial et al. Back in about 2010, 2011. And AWS, we first had AWS on the radar back in 2011. Now, this is a fun fact, and you can badger Sam Newman about this tomorrow when he's around. Sam Newman and myself were one of the four first ever AWS trainees in the world. Not trainees, trainers in the world. Because Thoughtworks sort of approached AWS and said, hey, you've got this, like, what appears to be a cool new thing. Maybe you should offer some training, because we'd like to send our people on it. And they said, well, no, we're not interested in that. We're interested in, you know, selling you DVDs and stuff, right? And maybe renting you some CPU. Not interested in training. So we thought, well, okay, well, we could do some training. So that's when we started doing AWS training. Lasted about 2 years. This is from one of the original slides, actually. Those are that's the journey AWS went on. And those were the partners at the time, the early partner network for AWS. It's changed a bit now. AWS reinvented a few more sponsors than that. But at the time, Thoughtworks, with our old logo, proudly sponsors of AWS. I promised to sort of, well, I mentioned I might talk about why AWS is a thing, or why AWS is going to eat your lunch. And I like this stickman thing. You know, there's a CIO and a developer, and the CIO says, hey, you know, developer, I just heard about this thing called a platform. Apparently it comes with a DevOps. You know, I think I'd like one of those, please. Apparently they make you go really fast platforms. And the developer says, yeah, sure, why not, right? Yeah, yeah, of course we'll have a platform and some DevOps. So why are infrastructure as a service platforms like AWS a thing? Well, it's because of this, right? Fundamentally, reductio ad absurdum, it's because they implement MMCQs where C tends to infinity. Now, obviously everyone in the room knows exactly what that means, so I'll just move on. No, I'm not. Seriously, I'm moving on. You can look it up, right? So then we had continuous delivery started appearing just after in 2011, which is, you know, the first time the book came out, first time we were talking about using, you know, as an industry, blue-green deploys, canary deploys, you know, single artifact promoted through build pipelines all the way into production, only built once, sort of auditable build pipelines and all these sorts of things. Microservices first appeared in late 2013. So this is before, actually, Martin and I published a paper. Microservices are getting a bit of a grilling at the moment. This is someone replying to a tweet of mine pointing out that every time they go for a job in a two-person company, they're often having to sort of work with systems split up into 10+ services with 10+ databases, and am I actually just trolling people these days? The answer is no. I still think they work in many circumstances. After that, we had Docker in just sort of mid-2014 on the radar. Now, Docker has only been around, like, while starting the adoption of Docker. This is not widely adopted at the time, since about 2014. That's kind of crazy, right? Because Docker and Kubernetes are synonymous now with how we do modern software delivery, how we do modern software engineering, how we do modern deployment of our applications. Kubernetes just after. Kubernetes was around about 2015. We started talking about that. Kubernetes now is basically how we run everything, right? React just after Kubernetes. I guess we could have kind of guessed that something in the React world would have, or something in the JavaScript framework world would have taken off. There's a whole bunch of sort of pointers to it. JavaScript is a first-class language. Treat all code with respect from UI to test. We were still doing server-side rendering the majority of the time back here, right? We weren't really doing much client-side. This is why JavaScript was like an additional thing, a little add-on. We sort of maybe wrote a test for, maybe didn't, right? As JavaScript started to become a first-class language, we started to see this, and with Node.js appearing, we saw this massive explosion in JavaScript. And, well, the JavaScript juggernaut rolls on. We have churn in the JavaScript world, overreactive. JavaScript tooling settles to merely chaotic. in late 2015. I love the old other Dave Thomas, brag Dave Thomas joke, which is around about 2016, I think he said on Twitter. I'm not sure what the correct JavaScript MVC library is to use because I haven't checked Twitter this morning. And that's kind of how it felt at the time, right? That's kind of how this world felt, this huge explosion in stuff that was being produced by the JavaScript world. But that's, 2016, React, that's when that sort of turned up. And platform engineering teams turned up in 2017. 2017 is kind of an interesting year because this is where we started talking about this idea of building teams whose job it was to build software to make the other teams go faster. So, looking after things like build pipelines and observability and these sorts of things. And then my colleague wrote a brilliant paper, which he wanted to call the half-arsed private cloud, but was sort of vetoed. It was called the superficial private cloud. And this is where, you kind of the idea that essentially you put an API over your ops team, and then you call it a platform as a service, and you're done, right? And yes, declare success, we now have a platform and probably a DevOps, and we're done. And I've seen this happen on a number of occasions. I remember going to a project, starting a project, and we said, we've got this requirement for a new environment. And they said, yeah, cool, well, you can use our API to create your environment. Well, fine, how do you do that? They sent us the kind of instructions, the tutorial or whatever, and we used it, and let's go with my environment. And it's like, excellent, what happened then? We got an email back that said, thanks for your request for an environment, that's going to take about 3 months. We thought, and they'd literally put an API over the top of ServiceNow, right? So we just hit a button that had pushed a request into someone's queue in ServiceNow, and the 3 months was the time it normally took them to procure that environment. So, this was the thing, the half-assed superficial private cloud, which leads to, the CIO says, I'd like a platform. I've heard it comes with a DevOps. And 2 years on, the boss says, well, okay, we've implemented a DevOps. We have a platform too, but we still can't get anything done. And I think that's because there's a big misunderstanding about what actually platform engineering is. And if you want to know more about this, I presume Liz is still around, so they are awesome at explaining what really good platforms look like. Now, I did say I wasn't going to talk about queuing theory, and I was going to leave you hanging there, but I've decided I probably should explain what I was talking about, MMC queues, where C tends to infinity and all that. So you think about queuing theory, essentially you have a queue of stuff that needs to happen, right? And you have a producer, or a number of producer, pushing things into a queue. So you have a rate of arrivals, essentially, the producers, which are lambda, and then you have a number of service nodes, known as mu, and then you have departures. And the rate of departures is dependent on, obviously, the number of service nodes and the length of time it takes to process each request that's in the queue. Kind of simple, right? So an MM1 queue is where you have a single service node servicing requests. Now, you can think of this as a very small company with a very small ops team of one person, right? You've got one person who's sitting there, and they take a request in for a new database server or whatever it is, and they go, oh, cool, right, I'll build the database. The database is done. There's one person in the department, and that's essentially an MM1 queue servicing requests to create databases. An NMC queue is basically a variable number of service nodes up to the number C. So you can think of this as a big ops team, right? Or you can think of this as Kafka with many consumers, the competing consumer pattern, if you like, from messaging. So a number of service nodes, each taking requests off a queue or taking work items off a queue, processing those requests, and that's essentially the service time. Now, when I said that why AWS is eating your lunch is because there are different sort of topologies, if you like, of combinations of platform teams and of sort of ops teams and of APIs, et cetera, et cetera, et cetera. So in a traditional ops team, you've essentially got an MMC queue where C is the number of people in the ops team. Right, so the length of time, the number of requests that can scale to be delivered by an ops team is dependent clearly on how long it takes them to complete a request, complete a ServiceNow ticket, but also how many people you've got. This is why it's expensive to scale operations, right? Because if you want to go faster in a traditional ops environment where you've got people doing work as a result of requests going into a ticketing system, you have to scale the people. And that's both expensive and time consuming. which is why, ops teams get to a certain size, and then we end up in the position where we're asking for an environment, and it takes 3 months. Get to the back of the queue, please. In the half-assed private cloud kind of version, it's kind of the same. Essentially, it's the same deal. You just put an API over the queue and pretend that the API is going to solve all your problems. So you're still in this MMC, where C is the number of people situation, and it's still expensive and takes a long time to scale. So for infrastructure as a service, and this is why AWS ate your lunch or ate ops teams' lunches, essentially they can almost scale infinitely. Right? The rate at which they can process requests is limited by the hardware, by the control plane, the data plane that they have available to them. Right? And so essentially the number of service nodes available to take to service requests to do stuff tends to infinity. Right? And obviously it takes a variable amount of time to actually execute those requests, but still, this is an MMC queue where C tends to infinity. Then you've got another sort of half-assed platform, which is a new anti-pattern we've sort of started to see, which is similar to half-assed private cloud, but this is where we pretend our platform engineering team are sort of self-service, but actually, when we ask the platform engineering team for anything, they have to put it into their queue and then execute that over a period of time as well. So it's kind of like doubling up on things. You end up with an API, you end up with a queue in front of your platform team, who take a long time to do stuff, and then you end up with a queue in front of your platform as a service, which doesn't take a long time to do stuff. But the problem is the people take a long time, so you end up in the same position as just a traditional ops team or superficial private cloud. So that's essentially the four sort of things I see in the wild when it comes to operations teams, and this is why AWS is doing so well, all the other cloud providers, specifically anything that offers self-service. And that's the key thing here, right? The MMC C10 to infinity, that's essentially a self-service mechanism. When I don't have to ask any human in the loop to do something for me, things get faster. And that's why we were able to go so fast, I think, these days. The other options are essentially expensive and slow. And this is why AWS is a thing. So that's the first of the curiosities. We're going to go back to the timeline now. So we had platform engineering teams. Just after that, well, quite recently, to be honest, we have data mesh. Data apparently is still a thing. You saw Dave Thomas's talk yesterday, one of the talks, which was brilliant, when he was talking about data centricity and actually looking for the data in your organization, because that's where the value is. And actually, I always have referred to data as the sort of ETL and all that sort of enterprise warehouse stuff, data warehousing, as the last refuge of the tiered architecture. Right, it's the last place where you have kind of business concerns haven't really started to creep in yet, and you've still got a bunch of bearded old people doing DBA stuff. This kind of a colleague of mine, former colleague of mine, Ian Cartwright, he talks about data and all the sort of the assorted stuff that you have in the sort of data world, if you like, as like pouring, especially in things like ETL and enterprise ETL tools, as like pouring concrete into your software architecture, right? Because as soon as you've got all this stuff linking databases with other databases, with data warehouses, it becomes impossible to change anything without having to change everything else. So the last refuge of the tiered architecture. Data mesh, of course, aiming to solve that. And then after that, we didn't quite miss the LLM. The LLM, so point in time where things started happening, we managed to sort of jump on that bandwagon, thankfully. We had things like Ernie and Bert appearing and a whole bunch of other stuff. We've got people writing about LLMs for developers. This is quite an interesting article by our head of tech, Zhu Hao, in China about how he's using a sort of context. He's using an LLM, which he gives loads of context to about the problem, the team shape, software architecture, the patterns they're using to implement some software, and then they use that as an extra pair of eyes over the course of their working day. It's kind of interesting. Of course, it's not all positive. There's lots of doom and gloom around. BT to axe 55,000 jobs, British Telecom in the UK. Kent Beck saying, I've just realised something like 90% of what I do is worthless now. And I was at an event where I saw this quite fun sort of head-to-head talk by two futurologists, one who was very much an optimist and one who was very much a pessimist. And the optimist was saying, well, the thing is, whenever we have these paradigm shifts in technology, whenever we have these brilliant big new inventions, right, what happens is they create tons of jobs, they create further innovation, and that kind of that kind of makes up for the fact that there's going to be potentially some disruption in to many employees and many employers. And he used the example, as people often do, of the number of cars in America. So after the invention of not the invention of the car, after the production of the Ford Model T, how many cars started to become available to the general public, and this trend was this huge upward trend, and it drove lots of innovation. People could go further, do more things, and whole associated industries were created. And then the other futurologist, who took a bit more of a pessimistic view, he said, yeah, but what happened to the horses? Right. The number of cars definitely shot up. But the number of horses, if you plot it on the same graph, took a bit of a nosedive, to be honest, in the same time period. So this is the question when it comes to things like, ChatGPT, LLMs, not artificial general intelligence. I'll get slapped from afar by Grady Booch if I mention that. But in terms of these sorts of advances, we don't really know what's going to happen, right? Because in this case, are we the horse or is it the car? Do all of our jobs disappear, or do we all get these new super exciting jobs? I don't know. So that's a bit about, I guess, where we've come from in the last sort of 15 or so years, maybe a bit longer than that, about 15 or so years. And I find it super fascinating that even in the last 2 years, we've had this giant shift in capabilities, in things like what large language models can do for us. And as much, I'm sure, as everyone else in the room has been playing around with it, seeing how I can use it in my day-to-day life, and it's super fun. I've been talking a lot about it. It's one of the first things in a long time that seems to have captured the imagination of the general public, right? The people who won't talk to us at parties, as Sam Aaron pointed out earlier in this brilliant talk. It seems like there were teachers talking to me about, hey, this ChatGPT stuff, should I be worried, what's going to happen when my students start using it to write essays? In fact, I've got one teacher friend in my local pub. I'm British, I have a local pub, there's lots of people there, but he's a teacher, and he's already running assemblies in school, for his students about the correct use of ChatGPT, what they can use it for, because they know they're going to, because they're kids and they're smart. So what can they use it for? So we've just had this incredible explosion in what's happening, but also the stuff we take for granted in terms of a lot of the tools and technologies are really, really close back in history to us. We're talking 2015 on for most of the things many of us use on a day-to-day basis. Things like Kafka, things like Docker, things like React Framework, and now things like data mesh, microservices, and so on. So the next bit I'm going to talk about is, I guess, building systems, optimizing for flow, or the subtitle is, Are We Software Engineers Now? And this is sort of riffing off the great Dave Farley's talk. He's written a book about this, which I'll reference in a minute, and riffing off his channel and some talks he's done online, where he points out that, in the past, we've sort of pretended that we're software engineers, called ourselves software engineers, but actually didn't really do any of the things that other engineers would expect to be doing as engineers. And my favorite example of this is there's an amazing woman I was privileged to meet in Chicago and then in Australia called Dr. Anita Sengupta. And she did a talk. She was the principal investigator for the Curiosity rover's landing bit. Now, I don't know if you recall how the Curiosity rover landed on Mars. It was pretty complicated. It wasn't just like through the atmosphere, landed on Mars. It was through the atmosphere, popped the heat shield, parachutes, which dropped to like a retro rocket carrying box down to about 50 meters. Then that lowered the rover on cables before the thing flew off. Right, that's severed the cables, flew off. And there's so much stuff that can go. As quotes engineers, really shivering at that kind of idea. So many points of failure. Right. She came to the end of a brilliant talk, which is available online, I'm sure. Came to the end of this brilliant talk. And she asked for questions, and someone said, right, being clever software person in the room, software engineer in the room, right, so what do you do about redundancy? They said, well, how much redundancy do you build in? Because you've got all these single points of failure. And she honestly, in Chicago, she doubled up laughing on stage. It was fantastic. And then she said, no, we don't really think about redundancy, because redundancy is weight, right? When we're going to space, anything that adds weight makes it much more expensive to get out of the Earth's gravity well, so we don't think about redundancy. We rely on a little thing we like to call engineering. And everyone in the room, 1,800 people in GOTO Chicago went, ooh. Walked out slightly embarrassed. And and she's fair to call that out, right? Because actually what we think of as what we do is a lot more like, I'm not going to get into the craft stuff, but a lot more like a craft than traditionally has been anyway. But I would argue, like Dave does, that some things have changed over the last decade, right? Going back again, the decade, a lot of the techniques on the radar that started appearing, continuous delivery, lots of automated testing, all these sorts of things, the different patterns for deployment, all of these are working to add predictability, reliability, safety, if you like, into the way we deliver software, into the way we build software and deliver software. I would argue, in fact, that if you're not doing a lot of this stuff, you're probably just, either in a position in an organization which won't allow you to, and you want to, or you're just being unprofessional. I was going to call it, right? Because there's so much, we've got this ability now to get stuff out into production in such a safe and reliable way, and tested to such a high degree, in an automated way, that if we're not doing that, I think we should be asking ourselves, why? Now, in Thoughtworks, I'm lucky. We have a bunch of techniques we've built up over time, a bunch of practices. We now call them our sensible defaults. You probably recognize many of them. Frequent and continuous integration. Frequent is in there to stop all the people shouting about branches. But don't use branches. Just work on trunk or master. Test room development. Pair programming. Build-in security in, of course. Fast and verified automated build. By fast, I mean super fast, under 30 seconds. Or for a fast build. Automated deployment pipelines, early and continuous deployment, quality and debt managed, and build for production. So build for reliability, robustness, and so on. This is the sort of list of things that are a minimum I would expect to see our teams doing. And if I do things like, I'll go in and sort of check every now and again that our project teams are working effectively, delivering the most value they can for our clients, and mentor them and help them and so on. And I always say, if you're not doing this stuff, or if you get questioned about this, or if you join a new project and you don't see this stuff, this should be raising red flags for you. These are the sorts of things where you should be actually like putting your hand up and going, like call for help, send the bat signal, because these are the red lines, if you like. These are our sensible defaults. And I'd go on to say there's a number of other sort of canonical texts, which I'll call out and I'll come back to. First is continuous delivery. This changed the game. Dan's talked at length about this over the years, but this changed the game when this came out back in 2011. I would argue that things like building microservices, and actually things these days like building evolutionary architectures from Sam Newman, from Neil Ford, Rebecca Parsons, and Pat Qua are also a part of this sort of canon now, because they talk about how, especially building evolutionary architectures, they talk about how we can automate some of the remaining hard stuff, which is things like governance, architectural governance, so how we can use things like fitness functions, which are essentially tests for our architecture and for cross-functional requirements that we can incorporate as part of our builds and use and run as part of our builds. These are sort of, again, adding to this canon that I think points at us being more towards engineering than not now. There are other books, obviously. Principles of Product Development Flow, the great Principles of Product Development Flow. This is the economics of what we do. This is why what we do when we work in small batches, when we have fast feedback, and so on. That's why that's economically more viable than not doing it, no matter what anyone says. Accelerate, so study on the set of practices that high-performing organizations use, and then team topologies. I would sort of categorize this, the stuff we do that seems to work, seems to make things safer, more reliable, lets us build systems in a more robust and reliable way, and then there's sort of a bunch of stuff about how it works. Right? This is how this stuff works, either economically or from an organizational performance perspective or from a design perspective. So the question, that Dave Farley asked, are we real engineers now? I'm not going to be unequivocal. I'm not going to be unequivocal. Okay, double negative. I'll be equivocal. That's the word I was looking for on that. I'm not sure. I think we're better placed to be on that. We're on that journey, and we're better placed than we were. So the next curious thing I'd like to talk about is why shared test environments should be nuked from orbit, and why it's the only way to be sure. Right? This is another curiosity. Or about how work flows as information through value streams. Now, I talked a bit about value streams in my talk yesterday morning. They've appeared in other talks as well. They appeared in Dave's talk. I'm not sure if any others, but certainly they've appeared a couple of times in this conference. I'm not sure if people really know what a value stream is or what use they have or how to create them. They're really, really simple value streams. They're from Lean. And the idea is you map out value-adding activity versus essentially wasteful activity or wait times. Right? So how much time we're spending for each activity that's adding value to a thing versus how much time that thing is waiting to have value added to it, if you like. Super, super simple. But we had this conversation in Thoughtworks about should we put this on the radar only a year and a half ago. And we were thinking, well, surely everyone knows about this kind of thing, path to production mapping, value stream mapping. Turns out it's a bit of a consultant's trick. And not that many organizations actually get to do this. It's one of the sort of superpowers I think I've got when I turn up at an organization is I often have the ability to do a bunch of stuff that no one in the organization has got time to do themselves. I was at UK government, GDS actually, it was the government digital service, and there's a brilliant manager there, one of the deputy director generals, and we'd been through an exercise, we were doing a fishbone stuff, and we did a value stream map, and he said, this has been a brilliant afternoon. He said, the problem is I'm too busy doing the work to understand how the work works. Right? I don't have a chance to take a step back and actually look at the system that I'm in and that the teams are working to. Right? And that's often what you get from consultants, but tip, give yourself an afternoon every now and again, and you won't have to pay my rates, which, as eye-watering as they are nowhere near as much as Dave's and Dan's. So, just saying. But take some time to understand how the work works. And value stream maps are a really, really good way of doing that. I mean, they're pretty simple, right? As I say, you look at value-adding time, and you look at wait times. And this is from a real client, anonymized, and this is the whole length of this is production lead time. And the way to read this is this way. The total value-adding time is the sum of the stuff on top, which is 5 days. The total wait time is the sum of the stuff on the bottom, and then the production lead time is the sum of both. So if you were thinking the first activity is software development, the second activity is testing, is coding, then testing, then deployment, you've got essentially 5 days for a work item, user story to go through this if all else were lined up. But actually it takes 47 days for the user story to go into production because of all the waiting. In this case, they had like a 2-monthly release cycle. So on average, there was a 30-day wait before they got into production. This is 42 days where they could have been making money on this feature. And often when you show people these things, people are smart, it turns out. It's quite a nice surprise most of the time, how smart people are. And when you show people how the work works, when you visualize things like this, or when they visualize things themselves, they're actually very quickly able to spot where optimizations can be made. Very, very quickly. It's, as I say, a superpower, a trick, and it's a way of avoiding having to pay my consulting rates. Of course, they're not as simple as that. I used this example yesterday. This is a value stream map from another organization that I worked in, which is a bit longer. Now, this is a 150, 170-year-old organization, something like that. It's got a bunch of stuff on here. It's requirements and business requirement documents this side, all the way through to production on that side. There's a bunch of stuff in the middle where integration happens and code is being written. But the important thing I want to refer to today are some of the symbols on this. Because there are 3 different types of wait time that you can often look for and look to optimize away, or look to actually work to reduce. The first is coordination. So this is where a team or an individual is waiting on 2 or more other teams or individuals to do stuff before they can get going. That's the sort of first type of wait time I'll call out. So this is a case where there was the developers. They had to wait on 2 types of data architects, each to update their own canonical models. Again, joke about that's not what canonical means. And once they'd all gone around in circles for a bit, then the software developers could actually write some code and so on. But they were blocked, entirely blocked, until those teams finished their jobs. The next thing is scheduling. So, scheduling, this is waiting for things like architecture review boards, change request boards, meetings. If you have a meeting that architecture review board that meets every 30 days, on average, it's going to block decisions going into it by 15 days, right? Because it's going to be half of it. This is often one of the simplest things to optimize away. Hey, if you meet twice as often, turns out your throughput goes up a lot, right? This because you're making decisions every 7 days, not every 15 days. Another consulting trick, which I learned from Dan, in fact. Daniel. So architecture review boards are a good example of that. And as I mentioned yesterday, change request boards in the research from State of DevOps predict, and I use that in the strict sense, predict low organizational performance. Queues are another form of delay. Putting things into queues causes delays. And you often see queues everywhere, and they're often hiding in plain sight. So, the business requests a change. You might think that's action straight away. No. There's a big, long list of changes that they might want to prioritize. That might happen quarterly if you're lucky, maybe 6 monthly, probably yearly. That's all stuff sitting in a queue. So if stuff goes in, it could be sitting there for an entire year. Worst case, it could go in the day before, miss the meeting, and you have to wait there longer than a year. You've got waiting for people to come up with options, architects doing stuff. You've got waiting for integration teams, work items flowing through, waiting for the integration team to pick stuff up and work on them. And sometimes we have all three of these things at once, all three of these wait conditions at once. And shared test environments should be nuked from orbit for this very reason, because usually shared test environments exhibit all three of these properties. You have to have scheduling issues, you have to wait for the other bloody team to sort itself out, right, and move off, because you've got a period that you're working in that integration environment. Right? You have coordination costs, because you're probably going to have to wait for that team to finish version 2.4 of their API and deploy it before you can, right? That's a coordination cost issue. And also you've got queues. You're going to have to put your work in and hope it gets to the front of the queue in the time that you've got accorded to you in your environment. So, nuke them from orbit. This is another one of the reasons that I love self-service infrastructure. Up to the limit of your credit card bill, we don't have to suffer this anymore. Within limits, we can actually use our own test environments within limits. Next is a sidebar, curiosity on generative science. This is something I've been exploring for a number of years now. It's interesting, generative science, because it's a way of sort of exploring phenomena in the real world using really simple models and simulations. I'll give you an example. This is a simulation of viral spread. So there's a few simple parameters, how close these little agents get to one another, how long they have to be there, and so on. And this is flocking behavior. I'm terribly sorry. This is birds. This is flocking behavior. So in this case, you've got very few simple parameters, same thing, same spiel, up until the point where I say distance apart, turn in radius, how far they can see ahead, and so on. Just by tuning these very simple parameters, you get these really complex emergent behaviors happening. And in the previous case, you didn't get that, because the parameters were just outside the phase transition between flocking and non-flocking, if you like. So this is one which is a viral load one, or how viruses spread. So this is very similar to the sort of the modeling that was done during the pandemic, actually. A lot of agent-based models were used to do modeling for the pandemic. In fact, Thoughtworks in India were responsible for building an open source epidemiological agent-based model to be used during the pandemic with a university out there. Using Rust, it's called EpiRust. And the reason is because if you're India, it's quite big. India's got lots of people in it, I think 1 billion and some change. And so you need to be able to model huge numbers of agents. And when you're doing agent-based models, there's always a trade-off between the complexity of the agent and the numbers of them you're able to simulate. And they were able to use GPUs and fancy modern hardware to scale this pretty impressively. Finally, I'll just give you an example, again, from generative science. This is the phase transition for oligarchic economic systems. You can put a very simple agent-based model together where the agents start with equal amounts of value. And then you say, right, run, and they do the sort of economic agent-based rational economic agent theory, whatever it's called, and they exchange value. And over time, every time, one agent ends up with all the value, all the things, and the other agents end up with nothing. And it happens every single run of this simulation, unless you put some controls in, And you can simulate the controls of Denmark, the economic controls of Denmark or the Netherlands or other countries, these ones on this graph. And when you simulate those economic controls, out pops the Gini coefficient for Denmark, Netherlands, the UK, the other countries. The Gini coefficient being the ratio of rich and poor in a country. Right. This is essentially, it's maths that says trickle-down economics is nonsense unless you have controls. The fewer will end up with all the things, which is fun in a generative science kind of way. Back to following the work, or why traveling slower. I'll go back, that's quite a nice phrase. Why traveling slower makes you go faster, and why queuing for lunch at conferences sucks. Sorry, it does, it just does. I talked about these 3 types of wait times. This is from the principles of product development flows. There's something like 187 or more principles in this. But I'm going to pull out a few from Don Reinerson's book to talk about some of the phenomena we see around us every day. So the principle of congestion collapse. When loading becomes too high, we see a sudden and catastrophic drop in output. Now, you can model this using turtles in that logo. You can show this using a very simple model of a road with a number of cars on the road. So essentially, as the cars for a particular number of cars on the road, going at a particular maximum speed with particular acceleration, so very, very simple parameters again, right? You can see this bunching behavior. Now, when you're on the interstate, when you're traveling by car, this is what happens when someone miles ahead of you puts a red light on, it goes ding, 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 ding. Suddenly, everyone goes to just to slow down, or even to come to a stop if loading's high enough. Right? Before ding, 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 all accelerating off again. This is a natural phenomena that's caused by there simply being too many cars traveling with a maximum speed of whatever it is. Like, it's just a sign of there being too many cars on the road. There's nothing you can do apart from reduce the number of cars or lower the speed. Right, lower the maximum speed the cars go, which is why on smart highways and things, you have this congestion, we're going to drop the speed limit to 40, because at 40 miles an hour, or kilometers per hour, you can support more cars on the road without causing this kind of congestion collapse. Now, why do I talk about that? Well, this is essentially what happens on our teams. You know, when you get into that situation where everyone's working like super, super hard, and just it feels as if nothing is getting done. Like, no work is actually getting out. Because when we start adding more and more work and people start working at 100% capacity on our teams, what happens is people get frustrated. People outside the team go, well, where's all this stuff I was expecting? And some hippo, highest paid person in the room, says, right, I need to prioritize this thing because this is really important, which adds to the congestion collapse and adds to the chaos. And this is why on our teams, often when we see this, it feels as if we're at 100% utilization, right, but nothing's actually getting done. It's because of the principle of congestion collapse. So I mentioned this already, the peak throughput control principle, control occupancy to sustain high throughput in systems prone to congestion. This is if we just simply reduce the number of cars that are able to travel on the motorway, then we get into this steady state. The phase transition isn't reached. We don't actually end up in this place where we're bunching. There is no congestion collapse. Just by reducing the number of cars or reducing the speed at which the cars are going. We can do the same thing by reducing the amount of stuff that's happening, right? The amount of unplanned work that's coming into our teams, pushing back on things like, reprioritization, so that we have to kind of reprioritize so this one thing gets stop the line kind of priority through a system and so on. Then there's the next one. And this is about lunch, you'll be pleased to know. The second queue size control principle, don't control cycle time, control queue size. I could equally say this about supermarkets and so on, but I like using conferences because they're an easy target in this regard, so sorry everyone. So how long did you have to wait for lunch? This is a simple question. You can plot this on a graph, right? So lunch is served at 1 p.m., say, and the number of people, the number of hungry people arriving for lunch, all right, just before the conference talks finish at 10 past, there's a steady number of arrivals. The system can cope with this number of arrivals. Then the talks finish, and everyone else piles in for lunch. And suddenly, what happens? We end up with a big queue, right? We end up with a big queue for lunch. It happens mostly every time. Now, the problem is because the rate of departures from that queue of people wanting to get lunch, the hungry people, the rate of departures from the queue is constant, but the rate of arrivals has massively shifted. You get this huge increase in the rate of arrivals for lunch. Now, the problem is what we often think about is, and this is like lead times, we talk about cycle time in the 4 key metrics. We'll control this by understanding what our cycle time is. And cycle time is a super useful metric, but it's a trailing indicator of actually what's happening in our system. If we look at the time it would take us to make a change to the system of serving lunch to people, if we use cycle time, we're not going to notice there's a problem for quite a while after the queue starts forming. So instead, what do? And this is what supermarkets do when they point video cameras at their checkouts. Right? They're looking for how much the queues are growing. Right? By looking at queue depth and how much a queue is growing, that's a leading indicator for cycle time blowing out. So we can do this again on our own teams. We talked yesterday, I think Dave mentioned yesterday, if you've got a backlog that's like 50 items long, there's just no point, right? Just delete everything after the 5th item, right? Because you're never going to get to it. Other things are going to get prioritized. Limit the amount of work that can be in progress or that's waiting to happen. By looking at the queue depth of work that's waiting to happen, we can much more easily control cycle time. And then finally, the batch size queuing principle. Reducing batch sizes reduces cycle time. And this is pretty simple to see. Again, you can look, if you've got, this is an example of 2 50% batches here, or if there's 100% of work items represented by these 2 triangles, then 50% is done after this time, 50% is done after this time, or another way of looking at it, we deploy here, and we start making money and all of that there. And then for that lot, we deploy there, and we start making money or bananas or whatever it is, coins at that point. But if you break these batches up, these work items, lists of work items up into smaller bits, like it's happened here, this is the same number of work items, the same amount of stuff, but we start making money on this batch here. And that money accumulates over this all of this time, whereas we've had to wait until halfway through. That's making money there, that's making money there. Just controlling batch size massively increases throughput without us having to do anything else. In fact, Don Reinhardt goes on, I love this quote, batch size reduction can enable us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization, which I think is not a bad thing. So, move on from that, sorry. So finally, I'm going to talk about how work works, which is what the conference talk was called. So it's probably a good idea to mention that. Talks about the domain model of everyday life. And I've been trying to understand whether you can use generative science and these sort of simulators to understand how what we do works in a sort of general case, right? Can we take things like these value stream maps, the activities that we perform on a day-to-day basis, different types of work that we do as knowledge workers, or actually factories as well, but as knowledge workers, can we turn that into a model that we can use to simulate and get some level of understanding of what we do? And I think you can. It's quite complicated, as you'd expect. But essentially what we do, how work works, is a work item comes in at one end, a business requirements document, and it's got a certain amount of information associated with it, a certain amount of value, right? And then it progresses through a series of stages, whether that's through, in this case, solution architects and options and designs, or whether it's an epic and a couple of user stories, and then finally into software development, where some code is written, and then some testing is done after or before, hopefully at the same time, before that work item is finally pushed into production, where it's got the maximum amount of value that it could have, right, hopefully, and starts making its money. That's essentially what our work is. We're taking work items and adding value to them incrementally over time by passing them through a series of value-adding, hopefully value-adding, or in the case of that very long, value stream map, not always value-adding activities, but activities that happen nonetheless. And I think if you can take some of the basically model some of these ideas, this is an example of the end. Thanks, Siri. I think. Okay. If you look at some of these different roles and what they do, if you're an enterprise architect, what they do, they take requirements documents and they take business requirements documents and solution designs, and they do stuff to them. They've got an inbox, essentially, and they're taking things up and they're going, oh, right, I need to do a solution design for this particular thing, and I'll turn it into that particular thing, a set of options. And you can take these sort of models and you can turn them into code, and you can write some code and you can create a simulator that does a bunch of stuff. And you can use various different ways of doing that. In the prototype that I've got, I use behavior trees, which are a nice way of modeling state machines. Essentially, it's what many computer games do. They use state machines as modeled as behavior trees. There's a bunch of other stuff. You can do goal-based planning and other things as well, but I use behavior trees. And I wrote a bunch of C# code to implement these behavior trees and implement these agents. And so now I've got a bunch of agents that simulate us doing what we do, right? Doing work, right? Turning things into other things. And okay, I'm not pretending to claim that we are actually as simple as these things, all right? No, obviously, and I'm not pretending that our teams can be represented exactly by these sorts of simulations. They can't. There's politics, there's people going, there's all sorts of stuff that's socio-technical that I can't necessarily model in a simulation. But I can't model everything about a bird in a flocking algorithm or flocking agent-based model either. But what you can do is take one view of the world and ask it questions and see if you can get interesting answers. So that's what I did, and I built this prototype. It's WebAssembly, Blazor, and it's a quick little demo for you. I appreciate them over time. But this is like two different teams. One's a waterfall team, one's an agile team. So what that means is one's taking 100% batches of work through a process. So everything has to be analyzed before everything is developed, before everything is tested. And essentially, just by running the simulation a number of times, that's literally the difference between agile and waterfall. So the red line represents the cumulative value delivered in the simulation by an agile team, by which I mean a team that picks up a user story, finishes the user story, or writes the code for the user story, deploys the user story, analyzes the user story, writes. Whereas the blue line is the value delivered by a waterfall team, by which I mean waiting for all the stories to be analyzed, followed by all the stories being coded up, having code written for them, being developed. Why couldn't I find that word in my head? Developed, that's the word I was looking for. All the work being tested, and then all the work being deployed. And you can see the average lead time, bit different. Lead time to get stuff done, bit different for that team. And the amount of value delivered by the team working incrementally and iteratively is ginormous compared by the time the waterfall team starts delivering any value. So I think at that point, I'm going to summarize. I summarise by saying a number of things. The first thing is I wanted to leave you with this thing about batch size. Batch size reduction enables us to shorten cycle time, often by an order of magnitude or more, without changing capacity or utilization. Right? Just deploying twice as often means you go essentially twice as fast, right, and deliver twice as much value. You don't have to add more people to a team, do anything other than deploy twice as fast. I think this is economically a fairly sensible thing to think about doing. Then we've got this set of books I've sort of referenced, continuous delivery, et cetera, et cetera, et cetera. I sort of said, stuff we do that seems to work and how it works. I think there's another group as well, which is the sort of underlying some of the principles behind this. So things like scale, study of complexity science, Quark and the Jaguar, again, about complexity, and this one by M. Mitchell Waldrop as well on complexity. Because all of that flows from a bunch of this stuff that underlies it. Finally, Lego. What would Lego do? Well, if you know what Lego did in the last 10 years, they moved from big batches, right? All the Lego in one big sets, one big bag for the big sets. They moved to the Lego pieces being in small amounts in numbered bags that correspond to steps on the manual. What would Lego do? They would reduce batch size. That's what Lego would do. And that means you build Lego faster. And anything that Lego do, I think I'm going to do as well. So thank you very much. That's me for today.